So here's what's new in version 1.0. So this video is going to serve as a bit of a walkthrough of everything that's new in version 1.0. It's mainly intended as a similar to the older videos of like version 7, 8, 9, and so on, where I updated everything that was new in those versions. So if you've been following along with SP Tools, this video is meant to kind of catch you up with everything that's new in version 1.0. But even if you're new to the package, this is still a good place to see everything that's new in this version in detail. So I'll go through all the bits here on the kind of text file and explain as we go. So the first thing, as you're probably aware of, is the name has changed from SP Tools to Datanaught. So there's a lot of reasons for this, but now that it's 1.0, I think it's time to have a new name. So there we go. It's now called Datanaught. So for detailed instructions on setting things up, I recommend watching the intro to Datanaught video. That'll show you the package manager and how to get everything going there. Main things are make sure that if you do have SP Tools, you uninstall that. I'm going to now show you how to adapt any patches that you have over to Datanaught from SP Tools and explain how to set some things up. So this first thing, in order to adapt your old patches. So here I have a patch that's one that I used for workshops back when I was doing SP Tools workshops. So if I open this, you can see I have a lot of missing items. Things are red. And if I look at the console here, it's really unhappy. So what I'm going to do is I'm going to close this again. Clear that. Now I'm going to open this up in a text editor. I'm using Visual Studio Code here, but there's all sorts of options. We basically want a text editor, not like this kind of text editor, like a programming text editor. Visual Studio Code is free, so you can use that. So if I drag this onto Visual Studio Code, what I'll see here is the max patch, but in text. So I can see all the, well, not really the guts of it, but this is what makes up an actual max patch. So what I'm going to do here is I'm going to rename everything that's sp.whatever to dk.whatever. So I'm going to click on search. I'm going to put sp dot, and I'm going to put replace with dk dot. So you can see here all the places that it wants to change that, which is quite a lot of places. So I'm also going to put the both of these things here. So this is matching case, and this is match the whole word. So we want that for both, and that's reduced it slightly. So this will basically rename everything that's sp.something to dk.something. Now it's worth mentioning here that if you have, this happened to me, if you have certain audio files, so for example, if you have an audio file called wasp.wave or whatever, this will actually rename that file. So you want to be conscious of what you do have in your patch. So save a backup of it before you do anything, but this will let you change everything in one go. So sp.dk. I'm matching case and whole word. I'm going to have a kind of quick look through here, make sure that there's nothing, like I said, with an audio file or something that is getting changed that shouldn't be changed. And when I'm done, I'm going to replace all. So 209 places. Okay, that's done that. And now I'm going to save this again. So I'll close out of that, come over here. Now if I open this back up, you can see it found everything. There's no red error messages, and all the abstractions are here. So that's how you edit all your old patches and adapt them to Datanaught. So next I'm going to explain some of the breaking changes. There's quite a few of them, and if you're interested, you can look through the changelog here for all the details. But they basically come into naming. So things that were called loudness, a kind of a generic name, I've named them a little bit more consistently with how they are named across the package. And same thing with units. So some units got changed. And the main one of that I'd like to flag is that the gain and decay sampler is now changed to percentage as opposed to dB. So 100% would be normal volume, whereas before 0 would be normal volume. So it was in dB. So that's one to be mindful of, but you can look through the rest of these to see everything that's changed. So now I'm going to explain about the synths. There's some things I'll explain first in terms of how all the different synth algorithms are set up, and then I'll walk you through the algorithms that are new. So I'll just open the first patch here. So this is DK AVDog, which is a simulation of the AVDog module within the Plumbutter drum machine from Seat Lombard. I'll explain in a second, but what I want to mention here is all synths have a dump message. So if I come here to the dump tab, I can see that I've got the algorithm, and if I send a dump message, it'll tell me the state of all the parameters within it. So I can change some of these parameters to something else, and then dump, and it'll update that. That doesn't seem that important now, but it'll make more sense when I'm explaining the regressor later. Additionally, they all have randomization options, so I can randomize the parameters and dump them, randomize, and it'll change the sound of them. I can also randomize, let's say 50% or 5% of what's happening. So these are things that are general across all of them. So the dump messages and random messages. All of them also take messages, so I can adjust the messages, and they also take CV inputs. So all of these synth algorithms you can see have many inputs. So we have, all the ones for messages, but then there'll be separate CV inputs for, in this case, pitch, rate, and Q. So that just makes it easier to interface with some of the other CV objects that I'm going to show later on. So that's some stuff that's generic to all of the synth algorithms. Now, in terms of specific algorithms, I'll explain some of these. So there's a whole bunch of Ciet-Lombard synths, of which I have a bunch of hardware of them. So a lot of these are just tuned and adjusted to like what the physical ones sound like as best as I can. I'm not a DSP, heavy hitter. So some of the specifics of like analog modeling, all that is a little beyond me, but in terms of the behaviors and the sounds, I think I did a quite good job of these. So there's quite a few algorithms here. So from the Plumbutter, there's 4 of them. We have the AVDog, which I'll show now. Then there's the Gongue, the Snare, and the Ultrasound. So this first one here is the AVDog. So AVDog is a self-oscillating filter that's meant to do these kind of slow undulation things. So you can read here a bit about it. And there's some links here if you want to learn more about how that works. But to give you an example of what this sounds like, if I just give it some triggers, it sounds like this. We get these kind of like wobble sounds. And, we can change the pitch, the rate, the Q. All of these things will affect the sound of them. So how long it resonates for, the pitch that it's doing it. So that's the basic, the kind of, I guess, pad, one of the pad instruments in the Plumbutter that generates these kind of, not melodic, but kind of harmonic, air quotes, language within the Plumbutter machine. Okay, as I showed here, you can have message inputs or CV inputs. Okay, and then I can trigger it with an impulse or audio input. So this is the same as what was in Waveguide Mesh from the last updates. So I can send just a trigger input, or in this case, I'm also sending audio input. So I'm using the audio input or a short moment from the audio input to actually trigger the self-oscillating filter. So you get some of the character of that sound. All of these have this combination Plumbutter. So this is kind of using the different components of the Plumbutter, but it combined. So I have a Gongue, I have an AVDog, there's another Gongue, there's a Snare, and an Ultrasound. So all combined, you can do some Plumbutter-esque type thing like this. All right, the dump message I already explained, and the randomization I already explained. So that's the first one here, the AVDog. Okay, so here we have the Gongue module. So this is the core kind of percussive one-shot module within Plumbutter. So you can use it for things like kicks or wood blocks or toms or any sort of percussive single hits like that. At its core, it's a self-oscillating filter, just like with AVDog, whereas as opposed to that one being built around having these kind of oscillations and undulations, this one's more meant for like single hits. So if I trigger this, you can see I get like kind of that low kick, and in this case, kind of a high tom. That's the sort of idea here. You can tweak the frequency and the Q and all of these things to adjust it. And just like with AVDog, there's a bunch of resources here if you want to learn a bit more about what all these parameters do and how they work and sort of philosophically where it's coming from. One thing to mention here is that this also has a bunch of different outputs in addition to the CV inputs. So we have the audio output, which there is kind of clipping because I've got it cranked up pretty high. I've got the impulse that was generated, And I also have this trigger and offbeat. So what this will do, I get a trigger when I actually trigger the sound. And I also get the offbeat, which is halfway through its cycle before it can trigger again. Which in this case is actually being used to trigger a second gong. So this is how it's set up in the actual Plumbutter. So there's 2 gong modules, and each one, whenever you trigger it, halfway through when it's ready to trigger again, it will output its own trigger. So you can kind of have them chained back and forth. So we get that second trigger here, and then you have the CV output, which shows you where it's going, and then it turns around. Then, as before, we can take message or CV. I can trigger it with the audio input or with just a trigger, and it'll just impart some of the character or the incoming audio to the resonant filter. And then the rest of the things are the same. We have the dump and randomize. Okay, so this is the snare module of Plumbutter. So what I did is I combined this with a Dunst module from Peter as well to give you some additional outputs here. So the core functionality you do, it will trigger snare sounds that sound very much like they do on the Plumbutter. So I spent quite a while trying to get that noise sound to sound exactly as it does coming from the Plumbutter. So it's a bit of a complex noise source. And then in addition to those outputs, we have these dust, pulse, ramp, and noise outputs that we do from the Dunst module. So as you adjust some of these parameters, it adjusts the density and character of these other things, which you can then use as CV. So for example, having the decay quite low, you can see you get these little dust particles. You get the pulse, which is, I guess, like a trigger, and then ramp, which is based on how the internal clock works within it. Like the other ones, message or CV. So this module has a bunch of different outputs that you can use to interconnect the different pieces. So decay, as I showed a moment ago, gain will be the volume for the snare output. And then you also have attack and release for the envelopes. You can also offset it and scale it. So you can use this to do CV type processing, both within the Plumbutter modules or across all the different synth algorithms within Datanaut. Then we've got the Plumbutter, the dump, and the randomize just as before. Next up, we have Ultrasound. So Ultrasound is a little different in that rather than being a kind of intrinsically sound generating unit, it's a filter. So in the Plumbutter, you have this ultrasonic filter in the middle, which is basically like an aliasing filter. It's a filter that's meant to alias the sound quite a bit. And in the Plumbutter itself, it's using the different roles, and it brings all that down into the audio range. That's not simulated here in Datanaut, but the filter itself is. So by default, you get this very aliasy, lo-fi sounding filter sound. So it sounds very similar to what you would get with sample rate reduction, but it works in a different way, and you get different characters with it. You can adjust the resonance, you can adjust the capacitor, which, you know, again, if you want to read more, you can look in there. And I've added some noise that you can add. This is the same noise that I'm using in the snare, and that's modeled after the Dunst noise. So you get some kind of interesting filtery sounds here. Like before, you have control over things with CV or with messages. So you can actually control the frequency with signal rate. So you can do like envelopes with that, which is kind of cool sounding. And then just like the others, you have dump and randomize. Now, in addition to the Plumbutter modules, there's also a couple. Now, these have existed in some of the musical examples for a little bit, but I've just done them again from scratch and a little bit better. So here we have the Quantussy. So what this is 5 different oscillators that are each modulating each other in a kind of circular sample and hold kind of way. You can read more about that here, but in effect, we have something that sounds like this. So Quantussy is really good for doing LFO type things as well as complex intermodulated kind of noise and patterns. And it has different outputs. So we have 5 ramp outputs, 1 for each oscillator, 5 sine wave outputs, and 5 square wave outputs. They're linked to the same thing, so those are all the same, except you have the different outputs of where they are in the algorithm, and depending on which ones you enable, you can get some pretty kind of complex sounds going. Okay, and I can adjust all of these things, the overall clock frequency, the overall chaos, which is how much signal is actually being fed into all the cross modulation, and then you have ramp and curve that affect the wave shape. You can kind of see in the scope there. It affects the lines of this is set to half, everything's triangle wave, and then I can kind of do fade in, kind of like shark fin kind of waveform shapes, and then individual rates for each of the oscillators. And they're all cross-modulated anyway, so all of them kind of affect all the other ones, particularly depending on where you have the chaos knob. But that's a Quantussy. Message versus CV, just like we had before. Now this also starts bringing some stuff where with all the CV things, we can use these different algorithms to audio rate modulate other algorithms. So in this case here, I have a Quantussy, kind of set, kind of slow, modulating a Rungler, which is then modulating a Just Friends module, which we'll hear in a moment, but this is a resultant waveform at the bottom, which sounds like this. So some pretty interesting stuff there. The different synth algorithms also have these upsampling options. So this is mainly for ones like Quantussy, Rungler, Just Friends, Mangrove, and 4Cs, where they're doing a lot of very fast changes. So the default, which is what it's set to, already has some upsampling amount. It varies per algorithm based on the CPU usage. But if you set it to none, it'll not do any upsampling. It'll be more efficient with the CPU. And if you set it to double, it'll be double whatever it is per algorithm. So all of these I tuned to have what I considered a usable sound at the, at a kind of believable CPU usage. So here I'm at 50%, which is, manageable. Again, if you want to use just a 4Cs and want it to sound really, really nice, you can put this at double. I won't do this now because you have to turn audio on and off, and I'm recording this video and that'll mess that up a little bit. But if you do want, you can upsample things and that'll sound a little bit better. And then here's a musical example where I'm using some Gongue drum performance, doing some analysis of it, and then mapping that to a Quantussy. So it sounds like this. Okay, so that's the Quantussy. Up next, we've got the 4Cs. So this is one that I've used in a bunch of examples before, but as I said, I've kind of built it again from scratch. So what 4Cs is, it's 4 different oscillators all bouncing off each other. So if I kind of find a spot here, yeah, there we go. So there's orange, yellow, blue, and red oscillator. So 1, 2, 3, and 4. And the frequency and amplitude of it is being set by whatever happens to be the oscillator above and below it. So I can adjust the slope and the rate of, let's say, this first oscillator, so the yellow one here. But ultimately, the frequency and the amplitude of it is set by whatever the second one is set by, which is then set by the third and the fourth. So they're all affecting each other in this way where you can see the orange and the green, 1 and 2 here, now both messing with each other. So if we listen to just the orange here. And if I just kind of randomize it a bit. I like listening to the middle ones because they're affected by the top and the bottom. So it's the third. You get some kind of interesting patterns there. And if I enable a few of them, and And just like with the Quantussy, this is good for both CV rate things as well as audio rate things. And it has CV inputs and audio rate outputs and all that. So you can use this to cross patch between things. Just like before, we can do messages or CV. Cross modulation, the same example I showed before. So we've got Quantussy modulating a Rungler, modulating just friends, modulating a 4Cs. And then dump and randomize is the same as before. And let me show you a musical example here. So this is similar to the Quantussy one where we have a gong drum. I'm doing some analysis here. I'm using that to map to a 4Cs, and then I'm applying the timbre from the spectral shape as a filter as well. And that's the 4Cs. Okay, so that's all the Seattle-Lombard synths, so quite a few of them. Now, after that, we've got a Rungler. So a Rungler was an addition that I wanted to add for a while, but I've found a version of it that I think works quite well, and I've mapped it in the way that I've done everything else here. So Rungler. So Rungler is similar to Quantussy in that it's a couple oscillators cross-modulating each other. In this case, they're cross-modulating each other with both analog, well, it's a computer, so it's all digital, but using audio as well as digital signals. So it does a kind of a cool thing that Rob Hordak worked out here. Again, you can read more here if you want to look at that. But what this ends up sounding like is a little bit more of a digital type oscillator. It's kind of hard to explain, but here, just have a listen. So you get this more noisy, digital, crunchy sounding synth, which I like quite a bit for a lot of the purposes in data knot. These are all the things that you can adjust. So the frequency of each individual one, how much they're rungling the other oscillator, so A to B and B to A. Then we have ramp and pulse width modulation for each one. And then you can adjust some of the routing options here. So there's quite a few parameters within this. Like before, we have both message and CV. Cross modulation. So this gives you some routing options that you don't often get with most implementations of a Rungler. So what this lets you do, it will let you choose the output that gets sent to the next one for rungling. So by default, they cross modulate each other using square wave, but if you want, you can have them cross modulate with the triangle or ramp oscillators instead. So that sounds like this. So quite different characters from that depending on which output is doing the cross modulation. Then we have sync outputs, which let you do oscillator sync as you typically would. Sort of a frozen type sound, but because it's a Rungler, it behaves a little bit more complicated than that, but I'll just show you what that sounds like. So depending where you set, you might hear it more than others, but it lets you sync the oscillators as you would with like a hard sync in a typical modular setup. Then we've got the dump and randomize like before. And then here we've got a musical example where I'm using this controller input to, if I move quickly, so this is using some CV objects, which I'll explain later on, it will trigger a new randomization. And then the position that I'm at will also do this float to binary thing where it'll turn on and off the sync and Rungler routing options. So. So that's the Rungler. Next, we have a few whimsical raps synths. So like before, these have been present there for a little bit, but now I've made them dedicated objects and done them a bit better. So first we've got Just Friends. So what this is by default, it's 6 oscillators, but you can actually change this using the trans message to have up to as many as you want. So 6 oscillators that are all synced to each other. So again, there's web pages here if you want to look at more at how that works, but let me just play and just show you. So something I added is I added some of the features of Mangrove into Just Friends and vice versa. So we've got the ramp, curve, and also formant, which is not normally in a Just Friends. When combined, sounds like this. So you get some different timbres that you typically couldn't. You also get different outputs here, so I can look at what the individual frequencies are for the different oscillators, which you can use then to map things. So the message versus CV is the same as we had before. These next few things are specific to how Just Friends works. So if you want to learn more about that, you can go ahead and look at the web pages. Whimsical Raps has a really good walkthrough guide on what everything in the Just Friends does. So I'll just explain it somewhat briefly for each of the bits here, and then you can go further if you want. So if I just turn this on. So what intone is, it adjusts the overtone series and the undertone series. So if I crank it up all the way, it'll be overtone. So you can see I have like the octave, then a fifth, and so on. And if I go down all the way, it'll be the undertone. So down an octave, and then I think a tenth or whatever it is, and then anything in between. So if I set that to default here. So it's going too fast to actually kind of see in those things, but that's what the ramp does. Now, one thing that's worth considering here is that these are free running oscillators, meaning that if I go back to 0 here, you can hear it's kind of quiet, and it's because they're all at the same frequency, but they're slightly out of sync because I changed the harmonic. This oscillator now is going a bit quicker, so when it returns back to 440, the phase of all of these oscillators is indeterminate. So if I want to resync them and have everything sound normal, there's a separate trigger input, which you can actually use to sort of do oscillator sync and all that. So that's the intone and the range. There's also an option here to switch between sound and shape. So that basically takes it from basically audio rate, like oscillator territory, to LFO territory. So I'm not really hearing that. But if I adjust these, you can basically have all these LFOs that are now harmonically synced to each other and adjust the kind of curve and the ramp time. So this is really interesting for doing modulation, where I can do all of this, and then I can also re-trigger them. So if you look at this last one here, whenever I trigger it, it starts its phase from scratch, which is kind of cool for doing envelopes. Now next we have timbre and formant. So as I said, that's something that's ported over from the Mangrove. So if I get a melody going, so here we can see the waveform a bit more. So the ramp affects whether it's doing ramp up or ramp down. Curve gives us kind of shark fin shapes, and then you can do combinations of them. And then the formant behaves as it does in the Mangrove, which at above a certain point, it starts folding things down. So it basically affects the pulse width, but if we go down, kind of starts doing these like octave jumps, which you start getting interesting timbres if you start combining all these together. And then combine that with intone. Okay, then we have mode and triggers. So this lets you switch between the transient mode and cycle mode. So by default, it's in cycle mode, meaning that it'll just run as an oscillator. But if I want to use this as an envelope generator, I put it into transient mode. And then what it'll do now, it'll generate all of these envelopes, but based on a trigger. So I can do this with a signal rate trigger or with a bang. So here I have the intone set to max. So if I put this to 0 here, all the envelopes will go at the same rate. And then I can adjust, you know, the tilt of them. So if I put it all the way this way, this one will go fast. And then just like with the other things, I can set the ramp and curve. I'll have these cascaded interrelated envelopes that I can trigger all at the same time. So here we have the cross modulation, which is more or less the same as before. We have the Quantussy modulating a Rungler, modulating a Just Friends. So I enable some of these. We get some interesting sounds. Dump and randomizer is the same as before. And then here I have a musical example. So what this is doing is every time there's a hit, it's setting a new random curve, ramp, intone, and time. So basically the frequency parameter here. And then every so often, it's also randomizing it by a small amount. So combined, that sounds like this. So that's Just Friends. So up next we have Mangrove. So that's one that's been around for a bit in a lot of the examples, but I've now made it its own object. Okay, so it sounds like this. So you have all the settings that you have from a physical Mangrove. And I also added some of the things from the PPM expansion that they've added. So there's additional outputs here. So if I switch some of these on, you can get some more complex waveforms by summing in the square, the pulse width, saw, and sine outputs. So like in all the other synth modules, you can control things with messages or CV. Which is great because you can do the audio rate modulation and cross-modulate between all the CV and synth objects. So here we have a cross-modulation example. So there's a Quantussy and a Rungler that are modulating a Mangrove, and then that's modulating a 4Cs. So that sounds like this. It also has the same dump message, and it's worth mentioning here that for many of the synths, you can dump the parameters, and then you can also use the parameter filter message. So let's say I want to ignore formant, barrel, and curve. If I set that and then dump, it'll only dump the things that remain. So that's useful if you're modulating things or if you're randomizing things and only want certain parameters randomized. And then to clear, it'll put everything back as it was. Randomize is the same as like everywhere else. And in this musical example, I've got an acoustic guitar coming into the onset detection. That's triggering some drums and bass every now and again. Then there's a melody being generated randomly from the incoming onsets. That's triggering the Mangrove with an envelope. And then that's also going into a reverb. So that sounds like this. So that's Mangrove. And there's one last new synth here, which is Waveguide Snare. So this is similar to Waveguide Mesh in terms of how it works, but in this case you get what's meant to be fairly realistic sounding snare sounds. So here I'm using a trigger as well as sending the audio input to affect the waveguide, and that sounds like this. So kind of what sounds like an acoustic snare drum. And I can adjust the tuning, the rattle, and the dampening. Like with Waveguide Mesh, we have control over the impulse parameters as well as the model parameters, so you can adjust those separately. And there's different input modes, again, like with Waveguide Mesh and with some of the other physical modeling ones. So by default, things are set to onset based, so it'll just get a trigger and it'll trigger it. But if I set it to real-time mode, we get some interesting behavior here where in addition to triggering an event, it will let the audio run into the waveguide the whole time. So we get what sounds like talking or singing into like if you have a snare that's just on. So that gives us this sound. So I kind of select this bit in the middle. If I put it to onset, this is the default behavior. And real time, which will just let it run the whole time. So it's quite interesting with, let's say, like vocals. So I run some vocals into this. It's like singing to the bottom of a snare, which is not generally desirable, but you know, it can be a sound. We get the dump message like before, same with randomize, and finally the musical example here. So here I'm taking a drum beat, and then I'm shattering it, so doing the NMF decomposition and sending different things to different places here. So some of it is going to a Seat Lombard gong, then the middle one's going to the snare, and then there's a shaker here. So combined, that sounds like this. And that's it for the synth algorithms. Up next, we have a new descriptor type, so spectral shape. So spectral shape comes in all the varieties that we have for all the other descriptor types. So we have spectral shape, we have spectral shape RT, we have class spectral shape. There's all the sort of permutations that you get with every other descriptor. So what spectral shape is, it takes incoming audio analysis as we would with everything else, and it gives us these different sort of spectral moments, I guess is the term for it. But it gives us a more complicated spectral summary of the different characteristics of the sound. So I have centroid, which you might be familiar from just the descriptors objects, and the same with a flatness. So centroid and flatness come from the same type of computation. We just get additional values here. So what spread is, this visualization here can kind of help. So centroid is that line there. So that is the kind of the brightness of the signal. Spread is how spread out this is. So if you imagine like a frequency spectrum, it's how kind of wide that bit is. So that's a spread. Skewness, which is the green one here, is this tilt, whether the sort of the sound is tilting towards being bright or tilting towards being dark. Kurtosis is a kind of a complicated one. It's kind of how peaky the sound is. That one's a little bit trickier to explain, but it does give you a summary of the information. Then we have roll off low, mid, and high, which represents the bottom of this blue and the top of this blue. So this represents all of, 95% of the energy is above that point and below that point. So if I play some of this drum machine here, you can see what this shows and listen to it. So this sound here was with a tilt pointing down. So this is kind of dark, which is also reflected in the centroid. The spread was still kind of narrow. And then here we have most of the frequency is above this and below this. So this lets us know that this was kind of a mid-range, low, dark sound that tilted that way. If we have a different sound here, so let's say I put, some beatboxing. So this first sound was actually kind of bassy like that. Let's put some of this snare here. This sound is quite a bit brighter, so we can see that reflected here. I'm gonna put something maybe noisy. So here this was almost broadband noise, and we can see that the centroid is kind of in the middle. The tilt is flat because it was, kind of flat. And then we have a very low roll off and a very high roll off, meaning that it was actually like a very broadband bit of noise. And if I let this play further on, we'll hear what that sounds like with this sax. So these really high, bright sounds you can see is very narrow. Most of the energy falls within that tiny band. The tilt is super extreme here as well. So spectral shape is more robust than the descriptors in terms of temporal analysis, but very different from the MFCCs in terms of temporal analysis. So MFCCs gives you a coefficients which collectively represent what the timbre is shaped like, but the individual numbers don't represent anything. Well, they do, but they don't represent anything kind of perceptual. Whereas here, the numbers give you a kind of a contour of what the spectrum is like, but these numbers mean something specific. So you can actually use these to map things to. So outputs, just like with other descriptors, we have a list, we have a buffer, a trigger, and a gate. So that's the same as we had in other places. Inputs, we have different input modes. That's the same. Different modes, so you can do amplitude or spectral, again, just like all the other examples. And then here's a musical example where I'm taking the 4Cs and then I'm applying the spectral shape analysis to a spectral shape filter. So this is a new object as well, where it takes the output of spectral shape and uses that to apply the EQ of that sound based on those contours. So that sounds like that. So you can hear the 4Cs is doing its kind of noisy thing coming from this mapping, but then it's also applying this as an EQ curve. So here it's putting kind of like a low frequency kind of sound. And then whenever the gong drum gets bright, you can hear the timbre jumps quite wildly, and that's because it's applying a different EQ. So not only is it affecting the mapping, it's also affecting the spectral shape that's happening there in terms of the filter. So that's the onset-based one, and then the real-time one, just to show a bit of that, does the same thing, but for real-time audio. So here's a musical example where I'm taking the spectral shape real-time analysis and using that to control a real-time filter. So in this case, it'll just be noise that's filtered by Gongue. So it gives you a pretty realistic and kind of musical filter that you can apply just from this spectral analysis. So that's spectral shape. Next up, we have this suite of CV objects. So there's a whole bunch of new CV objects that I've been cooking it for a bit, and I think finally put something together. So there's quite a few of them here. I'll walk through them, but basically they're meant for using with the different synth algorithms, because all of them have CV inputs and outputs. You can also use this if you're using an expert sleepers module or something like that and want to connect to physical hardware, so like your own module. Or if you're just doing mapping stuff where you want signal rate mapping. So that's the general idea of it. You can control and interplug within Datanaught itself, or if you're using like VCV rack or something like that, or if you have physical Euro rack module stuff. So to kind of walk you through these. So the first one here is cvcontrollers. So here I'm going to generate some fake CV. So imagine there's some CV coming in. So this is the signal that's coming in. And now we have all of these different outputs that are derived from that. So speed is representative of how fast the signal is changing. So if it's going kind of slowly and it's not changing very much, you can see the speed value goes down. And then when it moves a bunch, the speed value goes up. So this speed output gives you an overall sense of how active this incoming CV is. All right, next we have distance. What distance is the distance between whenever it changed. So, if it goes from there, then it goes to the next place and changes direction, that represents the distance value. So if it turns around, you see it turned around, kind of did a big change there. If I pause that, it doesn't really help. But it represents the distance between changes in direction. Time is the time between changes in direction. So if it stays going one direction for a while, the volume will be low. And if it changes direction very quickly, the value will be high. Then velocity is distance over time. So it gives you a sense of the velocity of the CV. And finally, we have the direction output, which is basically like, I guess, the raw direction. So changes in direction. So all of these outputs you can use to map to different things. And you can read here about a bit more detail of what each of those does. But this is really good for taking a single CV input, either from any kind of CV source, or if it's a controller input and deriving all of these things from it. So it has different onset modes. So by default, it's set to direction. So if I do a change in direction, even if I do it slowly, you can see that it reports a value here. So if I change just a small distance here, you can see that this distance metric is small. And if I do these big changes here, you can see the distance metric goes big. Okay, I can also change this to threshold. So what that'll mean is that if I do kind of these small movements, you see nothing is actually changing down below. I have to do, it's basically doing an onset detection. I have to do a big movement to have something report, which is kind of cool because then you can do all these sort of subtle movements and then have it only report a change when you do these bigger gestures. Again, depending on the kind of controller that you're using, this might be interesting. I use this quite a lot with a kind of a crossfader to generate signals where I can be moving around and doing stuff. Nothing happens unless I do a big movement, and then that triggers something specific. And then you can set the sensitivity and the lockout just like you can with the typical onset detection. What's going on under the hood is actually the same onset detection algorithm. So if I set this down to 25, it'll be not very sensitive at all. So I have to do very, very big movements. So I can do these kind of medium movements and you see it's not really picking anything up. Or the direction one, which will just pick up a change whenever you change in direction, regardless of how big or small it is. Now here we have an attack and release. So this attack, release, and offset and scale is consistent across a lot of the CV modules that'll just let you tailor the output. So here I have the fake CV being generated up top. I have the same outputs here, but now these are getting mapped to a Rungler. And then here I have control over the attack and the release time of those values. So I'll just let this run a bit. So you can hear that like the attack time matters there, and I'll adjust the release time. We can see the output here affected a lot in the direction output. So that's useful for tailoring the CV. I mean, you can also do your own shaping of the CV outputs using slide or whatever you want, but a lot of this stuff is built in. Now, offset and scale is similar to like what you use a lot in your Eurorack module, where you want to scale or offset the CV to what's most relevant. So here I have the same kind of thing. So the attack and release are both set to kind of a medium amount of time here, and I'll adjust the offset and scale so you can hear the impact on an FM synth here. You can see the overall range here within -5 to 5. So you use that to further shape the type of outputs that you want and what you're trying to control. Now with CV controllers, we have some polarity. So depending on the kind of input that you're getting, whether it's going from 1 to -1, you can set this to be unipolar, or whether you want it to be bipolar. So here I'm generating some CV that's going from -1 to 1, and I can switch between unipolar and bipolar. Now the main difference here is it'll affect how distance and then velocity are computed. So distance takes into consideration the total range available. So when it's set to unipolar, where it means it's expecting from 0 to 1, it'll take the distance as 0 being all the way down here and 1 being up here. Whereas if I set it to bipolar, it'll make that range be the whole range. So this you kind of tailor to the type of signal that you're expecting to put into it, but you can also adjust it to get some different ranges out of it. And then finally, here's a musical example where I'm using a whole bunch of things here. So if I'm moving in the left direction, I'm going to hear a Rungler. If I'm moving in the right direction, I'm going to hear Mangrove. And depending on where I am and the distance and velocity and time, all of those things, it'll modulate the parameters within the Rungler and the Mangrove. So you get some pretty sophisticated mappings just from a single controller input. Okay, next up we have cvcross. So this one is basically just a crossover filter. So all the low frequency will go to one output and all the high frequency will go to another output. So like literally a crossover filter. But what this does when you're doing CV signals is it lets you separate the DC offset, so wherever the CV lands, from the micro gestural language of it. Okay, so here we have the low frequency content and here we have the high frequency content. You can set the slew and the frequency for the crossover filter here. So here I have the same attack and release that I had before, but to kind of show in context here. So if I do very slow movements, you can see the low frequency changes and I have very little happening in the high frequency department. But if I move through these big movements, I can see the high frequency stuff come out and the low frequency represents where I rest. So it lets you separate the sort of overall position of where it is from the micro gestural language. We also have offset and scale just like before. So in this musical example here, I'm using the cvcross to separate the low from the high frequency. Then I'm taking the low frequency things and I'm running that through a separate CV controllers. So they're kind of cascaded into each other and that gives me this. So that's cvcross. Next we have cvgate. What cvgate does, it lets you send the CV to one output or another output based on a direction. So kind of like an onset. So if I send some CV into here, I can see it comes out of one and then it toggles over to the other. Then it comes back to this one. Basically just passing back and forth between each other. So the gate mode is identical to what we have with controllers. So I can set it to direction. So whenever I change direction, it will go to a different output. So if you look at the bottom, I'm in the secondary. And then if I change direction, it goes to main. Or I can have it change based on threshold. So if I do small movements, I'm just going to be hanging out in main. But if I do a big movement, it's going to jump over to secondary. So now I'm in secondary. And I can go back to main. And then it went back to secondary because I did a big movement again. So this lets you kind of juggle basically the CV from one place to another, regardless of where you are in the CV range, and have it either based on sort of passing a threshold or having a change in direction. So in this case, every time I'm going up, it's going to be in main, and every time I'm going down, it's going to be in secondary. You can get these kind of funky CV outputs from that. The attack and the release is similar to the other CV objects. Okay, offset and scale, again, same like the other objects. Okay, and then a musical example. So here I'm doing the same example that I did with the Rungler, but with a couple extra things. So whenever I do big movements, I'm going to randomize the CV. Whenever I'm changing direction, I'm going to send something to the cvgate output. So this one is doing direction, and this one is doing when there's a big movement. Sorry, this CV onset is doing when it's a big movement. And then where I am in the throw of it will affect this kind of 4-bit binary thing. So that's cvgate. And here we have cvonset. This has actually been the guts of a bunch of these so far, where it's basically doing onset detection, but for a CV signal. So we have very similar outputs to what we have with a DK onset. We have a bang, a trigger, and a gate. Then the difference here is that we have a direction onset and a direction raw. So those are additional outputs. So here's some fake CV. So whenever there's an onset for a CV, I get a trigger and a gate. And then direction onset will give me an onset regardless of what mode I'm in. So whenever it basically changes direction, I'll get a trigger onset. And then direction raw is the raw output, whether you went up most recently or whether you went down most recently. So all of these combined you can use to map things separately. Sensitivity is just like I explained with many of the other ones. So if I have the sensitivity set pretty low, not much is happening here. But if I crank the sensitivity, if I do a bigger movement, you can see I get a trigger along the bottom. Okay, or if I put it much lower, you can see I still get the direction onset no matter what, but only when I do a really big movement do I get an actual trigger output now. Okay, threshold and direction lets you change the mode of it. So direction is the default. Or I can set it to threshold, so it'll only do that when I do a big movement. Okay, attack and release, same as before. Offset and range, same as before. And in this musical example, I'm doing, whenever I move to the route in a big way, I get a snare sound. Whenever I move to the left in a big way, I get a kick sound. And whenever I change directions, regardless of how big the movement is, I get this hi-hat sound. And then there's also some kind of scratch samples that are getting triggered throughout. So I'm basically playing drums and snare, kick, and hat, and samples just from this one fader movement. So that's cvonset. And then there's two final ones here, cvscatter and cvsmear, which are the CV equivalents of DK scatter and DK smear. So what scatter does, it will take a CV, and whenever there's an onset, it will send it to a different output. So this is identical to DK scatter, but rather than being based around audio, in this case, it's based around CV. So the scatter mode, we can set, just like before, that we can do it by direction only. So whenever I change direction, you can see it goes to another output. Or I can put it for threshold. So only when I do a big movement. So now I'm in that 6th output there. If I do a big movement, it'll move to 7. And if I do a big movement, it'll move to 8. And so on. So this you can use to map, control all sorts of things, but just from a singular input. And here I'm showing it with the fader on the screen, but keep in mind that this could be actual CV coming in from Euro module, an LFO, noise source, or whatever it is you want. And this will just give you these other outputs or other CV signals derived from that. So direction and sequence. So this, again, just like in scatter, you can have it go in the order that it normally goes. So 1, 2, 3, 4, 5, 6, 7, 8. Or you can change the order. So I can have this go reverse. So it'll go here, it gives you the channel number that it's going through. Or I can have it be random. So I'm just going to go to random channels. I like using this mode sometimes because then it's just going to control different outputs, but not necessarily in a sequence. And if I want to, I can give it an actual specific sequence. So let's say I wanted to do 1, 3, 2, 3, 4, 6, 7, 5. It'll now do that as a pattern. Or if I want, I can go back to default. And let's go forward here. And now let me give it some audio. So what's happening with this example is this audio is coming through, it's getting split into a bunch of components, and then it's getting sent to different effects based on this scatter output here. Now, just like with scatter, I can do manual triggering. So rather than having the change from one channel to another being triggered by the onset detection that's built in, I can use this trigger input here to send it from a different signal. So here I'll just get some noise going and have some CV movement. Now I'm going to take the onset detection from this signal and use that to skip through the different channels. So it's jumping around randomly through different filters. Then we have attack and release, just like before. And offset and scale, same just as before. So in this musical example here, I'm using the scatter to control a just friend synth. So in effect, jumping through the different harmonics based on the direction that I'm moving in. And cvsmear is similar to that in that rather than sending it to different outputs based on the direction changes, it will send it different outputs based on the position. So if I send some fake CV here in, so based on where it is within the throw of it, so again, this is just like DK smear, it'll go either to this first, second, third, or fourth, in this case of having a 4-channel one. So there's 2 MC outputs here. The first one is the outputs with the envelope applied, so with attack and release. And then the second output is just the raw signal. So you can use both of these in conjunction. So you can see this one here. Whenever it switches off, we get the fade out. Whereas here, this is the CV that's coming out of it. It's just jumping straight down to 0. So you can use these in combination if you want. So the transition mode will affect how it goes from one to another. So by default, it does step. So as I move up, it's going to, at some point, just jump right to the next one. Okay. What the smooth transition will do is it'll basically kind of like crossfade. So you can see for a moment, both of them are active. So this basically crossfades between them. And then on top of that, you can use the attack and release, or you can have it be sudden. So with the stepping. So here it has a small amount of release built in default. So you can see we get a little bit of that tail there, but if I set it to smooth, they're both moving at the same time. And you can actually see the bigger difference here in the raw output. So here's a smooth. They kind of crossfade between each other. And if I put it to step, you can see that they suddenly pass from one to the other. Attack and release, just like before. Offset and scale, just as before. And then polarity, just like we had with controllers. So depending on the range that you're working with, you want to be able to set this to either be unipolar or bipolar. So unipolar between just 0 and 1, or bipolar if it's going between both. What's interesting here is that I can use a bipolar CV signal, so going between -1 and 1, and this is how it normally behaves. So you can see it goes from first, second to third to fourth. But if I set this to unipolar, I start getting this stuff where it'll wrap around and I start getting negative CV, which can be kind of interesting depending on what you're doing. So you can use this as intended, but if you misuse it, if you set it, give it bipolar CV, but set it to unipolar mapping, you'll get these negative CV spikes, which you can use for mapping. And then finally, the musical example here, I'm doing a similar thing with Just Friends, but rather than stepping between them, it's crossfading between them. Some additional things here. Trigger bounce and trigger cloud now have trigger outputs for chaining them together. So if I go to trigger bounce, so this behaves as it just normally did before. So if I give it a single trigger, it'll generate all these additional ones, but now it has this option for chaining them together. So in this case, I'm triggering an individual trigger bounce, and when that one is done, it's triggering a secondary one. And when that one is done, it's triggering the first one again. So this will just kind of carry on forever. And the same goes for trigger cloud. So this is mainly there so you can use it with the different CV objects. This pairs really nicely with the Plumbutter things. We're going to use the when it's done output to trigger a different event or a different sequence of events. So by default, trigger cloud does this. It's just kind of a cloud of events. So if I chain them together, in this case, it's a trigger cloud. When that one's done, it's going to trigger another one. And then when that's done, it's going to trigger the first one again. Low pass gate also has an offset mute now, so you can use it in a continuous manner. So if I go to LPG, there's this new offset mode. So here you can see it's being used as a kind of a, I'm using this ramp to control that as a like kind of a sweepable low pass gate. And again, just like before, this is meant to use with all the CV objects. And then you can also use trigger delay for some more CV processing options. So that's it for the CV objects. Okay, next up we have weights. This is something that's been added to all the Corpus and the concat objects. So I'll show you what that works. So let me find here corpusmatch. So inside corpusmatch, we have this new weights tab. So what this lets you do is adjust the relative weight of each descriptor that's being queried. So by default, if I put this to 100%, this will do normal corpus matching. So in this case, I have descriptors coming in from the Gongue drum. Using the pitch parameter, I'm replacing it with the sequence, and I'm doing find the nearest match within the toy piano. So that sounds like this. So I kind of select this section here. Okay, so let's say in this case, because I'm replacing the pitch with a sequence, I want pitch to matter a bit more. So I'm going to put this up to 1000. So what that'll mean is the pitch will be 10 times more important in the querying. So what this will do is it, because the incoming descriptors here from the Gongue drum doesn't have very meaningful pitch information, it's finding the nearest match, which in this case is kind of random because the pitch that it's finding from the drum is not really indicative of anything. Because I'm replacing this here, I actually want to find the nearest match And what this will do, it'll make the toy piano find this in a more meaningful way. So with this cranked up all the way, we get better matching on the pitch. So it's finding those a bit better. And if I want, I can adjust these to be whatever I want. So let's say I don't care about the loudness very much, but I want the centroid to matter a lot. I'll put this back to 100 here. Okay, and I can affect the color and the weight of each of the things. So let's say I don't care about centroid. I care about the noisiness a bit more. I care about the pitch a bit more. Loudness, if I put it to 0, it'll actually ignore it in the querying altogether. If I put centroid at 0. So in this case, I'm going to care about flatness and pitch. It's kind of interesting. Okay, and if I do the opposite now, I'll put the loudness cranked, centroid cranked, and I don't care about pitch or flatness. So it's finding the brightness and the loudness quite a bit more. So this is very useful for adjusting the color of the matching that you get. Okay, so that's it in corpusmatch. I can also do the same thing in concatmatch. So if I come here to the weights tab, so let me put this to 100 by default so we can hear the difference. So by default, if I'm just matching this sung vocal, I get this. Doing an all right job, but let's say I want the pitch to matter more and I want the pitch confidence to also matter more. So this will affect those weightings quite a bit more than it would otherwise. And that gives me this. So it's finding a lot more of that pitch information. And then just like before, if I want, I can fully ignore pitch and pitch confidence. And let's make the centroid really high here, and let's see what we get. The pitch is random in this case because it's not querying it at all. And then we get a lot of the squawks and stuff that are being resolved for the centroid. So if I put back here, let's say I want the loudness to be quite high and the flatness to be quite high. Let's see what we get. Interesting, a very different thing. But in any case, we can use these to further shape the matching that you get. And then we also have this option here, if I go back to corpusmatch, for inversion. So rather than finding the nearest match, I can find the opposite, so the furthest match. So here I have a section in the middle where it has a lot of repeating sounds. So if I do the nearest matching, that gives me this. Now if I invert the matching, I get this. So it's the furthest sound from what I was getting before. So in corpusmatch, this is useful if you want to get something that's not following the contours of what you're doing and you want to get something, it's not random, but it's sort of what's timbrally and loudness most further away from what you're doing. But I initially put that in specifically for corpusconvolver. So if I open that up, so if I come to the inversion tab here, what this lets me do is, so it's the same thing, but if I'm finding the nearest match, what I find that when doing this corpus convolution, so what this is, just as a quick reminder, I'm finding the nearest match in a corpus, I'm loading that sound in, and then I'm using that as an impulse response. So it's basically finding the most similar sound to what you're doing and then running your audio through it as an impulse response. So with this saxophone, it gives me this. So that's pretty cool, but because it's finding the nearest match, I find that like it kind of gets a little blurry and that it's the most similar thing. So what I found worked well here is if I find the most distant match, I get more interesting convolution in this case. So I'll play it again and then I'll switch to the inverted version. Okay, so that's the weights. Okay, up next we've got some new quirky effects. So the first one is onset freeze. This is something I've been wanting to add for a while, But I finally got it working to a point that I'm happy with it. And I'll improve this over time and change some things, but I think it sounds quite cool on its own. So the idea is here that you're going to be doing a spectral freeze type sound where you have a sound and then you're going to freeze what the timbre of it is and have that sustain infinitely. Normally when you do a spectral freeze, there's some latency because you have to capture a certain window of time and then sustain that. But if you have very short percussive hits, by the time that you've done the spectral freeze, the sound is kind of gone. So you sort of hear like an attack, then you hear a bit of silence, and then you hear the freeze. So I didn't really find that terribly satisfying. So onset freeze here, it does the same kind of thing, but rather than doing a real spectral freeze, it's doing spectral freeze. And by that, I mean it's doing a sort of a reverb algorithm that sounds like that. So here's some acoustic guitar going to it. You can hear the sound is just kind of frozen there, and we get a quite good sounding freeze sound. So I can clear it. In addition, I can just freeze manually if I want. And then you can overdub, and then you have different parameters here that you can shape with it. But the idea being that it's a spectral freeze, but they can respond instantly, effectively. Okay, so a bunch of parameters here to tweak, but I'll explain in the different tabs as we go. So we have retrigger versus latch. So what retrigger will do is that every time there's a new hit, it will do a new spectral freeze again. So the spectral freeze will go from tip to tail, and we'll just get constantly a new spectral freeze happening. So with this Wurlitzer here, we get this sound. When I set it to latch mode, what it'll do is every other hit will do a freeze, and then the next hit will toggle that freeze off. Then the next hit will toggle the freeze on, and the next hit will toggle the freeze off. So we basically get a kind of a latching on and off thing. So that sounds like this. So that's how the latch works. Now, since under the hood we have a reverb, we can actually adjust a lot of these reverb settings. So in this case, I have the some of the parameters set here. So the feedback, the damping, and some of the EQ settings are set in a certain way where I have a spectral freeze / reverb, where it's going to do a kind of a bit of a decaying reverb tail, but rather than being an actual sustaining reverb sound, it's just based on those momentary onsets. So it's kind of like a hybrid between a reverb and a spectral freeze. So you have that kind of combination where it's doing kind of a reverb type sound, but instead of the reverb getting all muddy and sustaining as it typically would, since each one is an individually frozen thing, we have this kind of reverb where it's sort of cutting itself off, essentially. And then you can adjust all these parameters here to get different settings within that, adjust the tilt, and adjust all those characters there. But you can get these kind of interesting reverb-ish type sounds. Next, we have this envelope. The envelope is what's applied to the actual algorithm going into the reverb. So if I have this kind of attack and release set going into the reverb, that'll make for a softer sound that's going into the actual freeze. So in this case, I have the attack and the hold set quite mild here, so at 50 milliseconds. And that gives me, instead of this like kind of sharp freeze sound that I was getting before, it'll get this kind of slow fade in with the actual freeze bit. So because at the core we have onset detection like we have elsewhere, we can use the every and probability parameters to affect how often it works. So by default it's 100% and it's every time, so every one it does it. So that sounds like this. And in this case I'm in latch mode. So if I put this to 50-50, or if I put it to 50, half of the time it will actually trigger. Or if I put this back to 100, but I do it, let's say like every 3, every third one it will then trigger. Or if I do a combination. So if I do every 4 at 50%, every fourth attack, it will have a 50% chance of triggering. So you get these kind of nested probabilistic behaviors out of this. So what we have in this one here is if I set it to manual 1, rather than having the incoming audio determine when the sound is frozen, I can have one set of audio. So in this case, I'm using a Wurlitzer as just audio input to it. And then I'm using the onset detection from this Gongue drum to trigger when audio is actually frozen. So in this case, the audio that's going into the algorithm is a Wurlitzer, but what's triggering the freezing is the rhythm from this Gongue drum. So that sounds like this. So here we have the different input modes, and this is what we can use across all the different descriptor and onset detection algorithms. We can use the first input for onset detection, but then use a separate input for the audio analysis. So you can use this with the different input things, and you'll get different sonic character from what's being frozen versus the thing being used to detect the onsets. And then finally, here's a musical example. So in this case, there's multiple onset freezes in here, all being triggered by these cascading behaviors. And that sounds like this. So that's onset freeze. Next we have onset tap. So onset tap is a kind of an odd effect here. What it does, it lets you store taps, almost like a multi-tap delay, but based on audio onsets. So whenever there's an onset, and then it will keep a certain amount of these onsets frozen. So by default, it's set to 8 taps of up to 250 milliseconds each. So that means every time there's an onset that comes in, it will store one of these things in a tap and then make them available for triggering at a later time. So it's kind of tricky to explain, but let me show you what it does. Okay, so here I've recorded a bunch of taps into it. Now, once they're recorded in here, I can trigger them from the keyboard or with the mouse, or this can be numeric input from anywhere else in Datanauts. So for example, from a classifier output, from any sort of trigger thing. And what's interesting is that this will replace it. So if I put some new audio into here, let's put some, let's put the Wurlitzer, play a little bit of that into it. Okay, and let's switch this over and put a beatboxer. Where's that? Let's put some gong drum. Well, let's put this drum machine. Now all of those are mixed together. And what's cool with this is that you can still keep playing it while it's recording new taps. So if I put the, let's put this percussive vocals on here. So I'm going to let it run, and then I'm going to play just numbers 1, 2, 3, 1, 2, 3, 1, 2, 3 over and over on the keyboard. So you can see what I'm triggering actually gets cycled out every time. So we can use it in kind of perpetuity as a way to have audio that's coming in that's available kind of for live sampling. You can maybe think of it, where you're basically storing all the most recent onsets and then having them available for immediate playing. So the playback settings here, it's using basically Corpus player as the core playback unit. So you have control over speed, start length, all the kind of things that you have with a typical sample playback. So I can play these back slower. I can put a fade in, if it, a fade out. Well, there's already some fade out by default. All those different things that you can do with the sampler or Corpus player. So what gets recorded into the different taps is set by the tap mode. So it could either be length, which is a default, or gate. So length will do, like we have in this first tab here, it will set the maximum tap length. So if I set it to 250, each tap can be up to 250 milliseconds. If an onset happens before that, the onset tap will be the length, or that specific tap will be the length of whatever that time was. But if no new event comes in, the tap will be 250. Now, if it's set to gate mode, what it'll be is the gate length will set the duration. So this is useful for kind of more percussive, shorter sounds. By default, it's set to 150% of the incoming gate from the onset detection, and that'll sound something like this. So here with these short sounds, I can, if I trigger these, you see they kind of variable, but they're based on the gate length that came out of that. So if I put this to be 100%, it'll just be the raw gate length. So I'll just play maybe from later on. Okay, so depending on what you need, you can use either the length or the gate mode. The default length is what I most often use, but the option is there. Now the record mode will deal with what happens when you use up all your taps. So the default is cycle. So if I have 8 available taps, what it'll do is it'll record into the 8 taps. And then when it finishes the 8th one, it'll go back to the first one and go again. If I set it to one-shot mode, what it'll do is it'll record only however many taps you've told it, and then it will stop. So in this case, I have it set to one-shot mode, and there's 8 taps. So the first 8 things that happen will be recorded. And now, even though audio is still happening, you can see no new taps are being added. So now I have these 8 taps that are just frozen in time. This is useful if you want to kind of stop recording after a certain amount of events. I can clear it and then add more. Now, separately from one-shot mode, if you want to, you can freeze the taps that you have. So here I'm not in one-shot mode, I'm in the normal cycle mode. So while I'm adding new things, let's say I'm happy with the taps that I have in there. So if I'm just playing, I'm like, okay, I like this setup, I can freeze. And what this will do, onsets are still being detected, but I'm not adding any more to the taps. And I can play some more audio here, and once I'm, let's say, want to add more things in, I can unfreeze, and it'll keep adding to the taps that I have there. And freeze, and let it go some more. So what freeze lets you do, it lets you take the state of the current taps and lock them in. And just like with onset freeze, we have probability in every, so we can set it to happen 50% of the time, or every third one, and that just gives you a different behavior. And similarly, we also have manual triggering. So in this case, I'm going to be sending audio into it. I'm going to turn on this metro, and what this will do is it'll, every 250 milliseconds, it'll record a new tap, as well as making a random flurry of note events. So that sounds like this. Okay, we also have the different input modes as we have elsewhere. And then finally, here's a musical example. In this case, I'm taking some incoming onsets from Gongue, and I'm using the onset detection from that to trigger a growling bass and a carpla strong. Then I have some voice recordings that were just set into here. So there's 16 taps of voice that have been recorded, and that's just been kind of frozen in time. So these taps were generated when the patch loaded up, and they're just stuck in there. And now there's this sequence that it's going to run through, and that sounds like this. Next up, we have the refer message. Just like weights, this is something that's been added to all the Corpus and concat objects. So let me go ahead and open corpusmatch. So inside corpusmatch, if I go to the refer tab, what refer lets you do, rather than doing a corpus analysis, analyzing a corpus, saving the JSON file, loading the JSON file, refer will let you bypass all of that and just analyze very quickly and make available for corpus playback audio that's in a buffer. So here I have Gongue loaded in a buffer. So if I refer Gongue, it'll take a moment to analyze, and now it's available for playback. And if I want, I can do the corpus-based matching as I normally would. And I can do this with any buffer. So here I have a longer one of voice, so I'll refer that. It'll take a moment to analyze, and once it's done, as before, I can use that right away. So depending on how big the buffer is, it might take a second or two, But again, this bypasses the need to do an offline corpus analysis and then load a file. So let's say you're doing some live looping or some live recording in your patch and you want to make what you've recorded available right away for doing this. You can just refer a buffer and it'll become available right away. And you can even do that while playing back. So if I'm playing here with the voice one and I switch this to brushes, you see I kind of like missed a couple hits while it was loading it, but you can still just have audio running and doing stuff. Now the refer message has a couple arguments. So if I set one argument here, it will let you set the length of time in that buffer. So if I do Gongue 2000, what this will do is it'll take the first 2 seconds of Gongue and then have that be available. So rather than the whole buffer. And this is useful if you have something like Karma where you have a buffer that's like a minute long, but you've only recorded it something like 10 seconds long. You can just do refer whatever the buffer name is and then 10 seconds. And then that'll just make that bit available in corpusmatch. If you send 2 arguments, you can set the start and end point. So you can get a little bit more detailed in terms of like, I want only this bit of the buffer available for corpusmatch. So let's say I only want from 500 to 8,000 milliseconds of the voice corpus. And then you can do all the typical corpus stuff beyond that, like do the filtering and weights and everything else that we've talked about. So I can do the same kind of thing, but with concatmatch. So let me open that up. So if I go to the refer tab, I've got the normal concat pipeline. I've got concat analysis, concatmatch, and then concat player. So if I refer Gongue, it'll take a moment, and then now that's available for concatenation. Or if I refer voice, that'll take a moment to analyze, and then that becomes available. And just like before, whilst audio is happening, I can actually refer, and it'll take a moment before it becomes available, but audio can still keep happening. So you saw the concatenation stopped for a moment because voice is slightly longer. I think it's about a minute. So it took a little bit to run through that, but the audio playback still kept going. So you can do what you're doing, refer a buffer, and then carry on. And just like with corpusmatch, you have the additional arguments. So I can refer just the first 2 seconds of it or from here to there. And this lets you, again, if you're recording in a buffer and you only want to use a certain section of it for concatenation, you can do that. So another thing I've changed here is how creating a corpus and creating a concat corpus works. From the beginning, the way, the kind of paradigm that I typically use, and my expectation was that if you were creating a corpus, you would load a folder of individual samples, and that would be what you would use for your corpus matching. Or if you wanted to do concatenation, you'd use a single long file, and that's what you would use for your concatenation, because that was my typical workflow. What I've changed now is that you can load a folder or a file into either of them. So if I go to corpuscreate, I now have the option to read folder, which is what read used to do before. So if I read folder here and I select, let's do speak in math because it's small. I'll do that. That analyzed real quick. I can see that analyzed all those files. Now, instead, if I want to read a singular file, and I'll come here to musical examples and let's load this voice sample here. So there's about 50 seconds. What it'll do, it'll read through it, it'll find all the onsets, and then it'll analyze them as it would for everything else. So it's done, and these are all the onsets were detected within that singular file. Now, if I write this to disk, it will load this and it will behave like a normal corpus analysis, but rather than having come from a folder of samples, it's come from a single file. Now, along with that, if I go to concatcreate, I can do the same thing. So here the default was read. So if I read a singular file, so in this case, let's load something kind of short and do this novelty example here. So just 20 seconds, I'll analyze that file. Okay, so it's done. But now if I want to, I can read a folder. So in this case, I'll do the speak in math just like before. What this will do, it'll put all of those files in a single buffer and then treat that buffer. And again, if I write this to disk, it'll then behave as it would normally otherwise. So once you read it, you don't actually have to be concerned when you load it and that it behaves any different. So if you're using concat synth or concatmatch or concat player, any of these things, you just load that created concat from this and it'll behave as it would otherwise. So this folder and file thing just lets you load folders or files into corpus-based or concat-based playback. Okay, next up we have regression. This is a completely new thing that's in here, and it's part of the reason why I built all those synths that I explained earlier, is that I wanted to have built-in synth algorithms to do regression. So what regression is, it lets you map from one dimensional space to another dimensional space, which is kind of vague, but in context what this means, it lets you take either descriptor inputs and map those to controllers, or controllers inputs and map those to synth parameters. You can basically map any set of numbers to another set of numbers, is the basic idea. So the way that this manifests most concretely in Datanaught is if I open up DK Regressor. If I come here to the Gamepad tab, that'll let me show these things off. So here I have a Quantussy being controlled from this mouse input, or if I had a gamepad that would do the same. And here's a Rungler. In this case, what the regressor is doing, it's taking this 2D input and sending it into the regressor, and then it's taking the output of that and then using that to control the synth. So the most common use case within Datanaught is this idea of taking some kind of controller input and then controlling a synth with it. Now, the way this works is if I open up Regressor Create. Now, the reason that all the synth algorithms have those dump outputs is because it makes this kind of training much, much easier. So when you're training a regressor, you typically have to scale your values into a certain range for the input of the regressor and then scale them back to your normal range. So for example, if I'm controlling an oscillator that's in Hertz, so that's like up to 20,000, but then another parameter is in dB, so that's like negative numbers. Another one is just a toggle between 0 and 1. All of these are in wildly different ranges, so you kind of have to scale them, and it gets a little unpleasant to do all of that. So what this does, it sidesteps that. So I'll just walk you through this quickly here. So if I open this gate so I can hear the synth, okay, I'll just kind of randomize it a bit so we get a different sound. Okay, that sounds kind of interesting. I want to take this and I'm going to map this area here to control the synth. So if I put this in this top left corner, I'm going to use the dump message. So this is the parameter names in their current state. I'm going to add point. Well, I'll put this where I want it, and then I'm going to add point. So if I print and I look here in the background, I can see that over here I have all the synth parameters, and I have the position on that grid that I did. All right, so let me do that a couple more times. All right, let's take this kind of high-pitched one. I'll put my controller here. I'll dump. I'm happy with that there. Add point. Okay, let's find another random one. Sure, why not? Okay, dump. I'll put that here, and I'll add point. And let's add one more. Okay, why not? I'll dump. I'll put this here, and I'll add point. So now if I print, I have 4 things here. So 4 sets of synth parameters and 4 controller inputs. Now if I turn this on and train, it trains super quickly, and now I can control the synth. So the inputs and outputs here can be anything, and if you want, there's a whole separate regressor tutorial that you can watch that'll help clarify a bunch of this stuff. But all of that is to say that regression is something that's brand new, and the dump message and randomization stuff was made specifically to do this. You can also do this with Max for Live devices using this M4L helper. So with that, I can do dump messages from any Max for Live device. I can randomize it, dump the parameters, randomize, dump, and all that will work. Similarly, if you have plugins, you can use this VST helper. This will let you randomize and dump parameters for any VST or an AU or whatever you want to load. And if you have your own synth algorithm or you want to do your own dictionary, you can set a definition here where you have your parameter name, your low and your high range, and then generate a dictionary, which you then create values for. And then this is what you connect to Regressor Create. And then within Regressor itself, I'll just show one more time by opening that up. You have a lot of options for how you use it. So there are several outputs here. So the default was meant to be connecting just a regressor directly to a synth algorithm. It'll send pairs of values where you have a parameter name and then a value. So this is sending rate and then a value, then it's set rate B and a value, rate C and a value. Then there's other options if I'm doing, let's say, a laced list in this case, where I want to set all the parameters at once and then I want to ping a low pass gate. So that sounds like this. So I'm setting all the values and then I'm pinging it. And then I have this other output here for raw list. So I turn this up. have a list of values that I'm just sending out, and then that's controlling this synth directly with the list. So there you have a bunch of options here for what the different outputs are. You can also control the regressor with different inputs. So in this case, using descriptors instead of a controller. So I've got this training here that I've loaded up, and now I'm using the descriptors input from Descriptors to control Quantussy. And that sounds like this. So here I have a musical example where in this top left quadrant, I've got a 4Cs. On the right, I have Gongue. On the bottom, I have Plumbutter. And on the left, I have Quantussy. So I can move around this whole space. The audio from Gongue and Plumbutter are also going to be quantized, like rhythmically, which is kind of interesting. But that sounds like this. Or if I turn on this automatic one. And that's regression. So there's a lot of new features specifically for using with a gamepad, and they've just been built into the existing framework. So if you use grid scale has a bunch of gamepad specific additions now. So if I come here to the gamepad tab, there's a few different things. So here, if I have my gamepad hooked up, if I move my left analog stick, I could control things. And I could zoom in by clicking in. So here, if you have your gamepad plugged in, you can use these different things. But if I come here to transformation, I'll explain these in detail. So some of the additions are the ability to map a circular space to a square space. Now this seems kind of funky, but if you have a gamepad and you're wiggling around in a circle, you have input that looks like this. So if I put this to 100%. Now, if you're using that to map to a space, you can't actually ever get this corner value. You may not really notice, but if you plug in your gamepad, you can't ever get like -1, or 1 and 1 or whatever. So what circ to square does, if you enable that transformation, it will map a circular space to a square space. So depending on how big or small you do it, you can see it's kind of taking the circular mapping here and making it more of a square mapping. And then you can also transform back using square to circle. So if you have a square input, you can transform that back to be a circular one. So here I have square to circle. I'm moving a square shape here, and if I make it kind of big, you can see it's mapping it back to a circle. And it's doing this kind of movement there. Another thing that's been added is you have the option to control separate XY inputs and output ranges. So that lets you do this, what I showed in the last example, where I have a subset of a space that I'm mapping. So I have the XY in of that range, and then that's being mapped to a whole separate output range. So that's quite useful for having subsets of space that you can then use to control multiple things. So if I load this corpora, so in this case I have a voice corpus, then I have Gongue, then I have a Plumbutter, and then I have Quantussy. So those are the new additions in grid scale for gamepads. Okay, next up we have Plotter. Plotter has been pretty severely overhauled. So if I open up Plotter, so it works as it did everywhere else. The main thing is that it just looks different and behaves a little bit differently. So if I load up a Corpus voice here into corpusmatch, you can see now that it's colorful by default. So rather than being the white background with black dots and it's just a 2D grid, by default it will be a 4D representation. So I've loaded up a corpus into corpusmatch. This voice has been analyzed in a multi-dimensional way, and corpusmatch always scaled that down to 2D in order to display it in the kind of plotter. The difference now is that it's scaling it down to 4D, where we have X and Y as it did before, but then we also have color and point size. So all this stuff I can use as before, but I just have a different look and more rich information. So rather than the position, the X, Y being what matters, we also have the dot size and color that you can use. So if I look here for classification, When you're loading a classifier, it will do the old school thing where each color represents a class. So rather than doing different size points and different colors as with the kind of corpus matching thing, when you load a classifier or a cluster thing, it will actually show them as the individual colors per cluster or per class, just so the behavior is consistent with what it should do. So if I go over to color and size, I now have different size options. So if I load this corpus, I have a small, a medium, a large, and there's an extra large as well if you're doing mouse-based playback and you want to use a lot of your screen. So all of these work as you would expect them to. And now we have the option to load different color maps. So we have the rainbow one, which is the default. If I set it to linear, this gives me the most perceptually correct version where the colors are perhaps not as spectacular looking, but the distance between the colors as we perceive them is mapped most accurately to the distance between the actual points. So rainbow is the default. And then you have all these different options. There's a grayscale and a colorblind option, and HSL is the most bombastic in terms of color. Now, all of these, in addition to being able to set the different color mode, you can set an additional offset. So here is HSL, the default, but if I set this offset and I put it, let's say like 0.5, it's rotated that whole color map. So you can see it looks radically different. So it's the same sort of 4D representation, it's just kind of rotated the color map part of it. You can set the different positions. Oops. And you'll just get a kind of a different feel for the color. And then finally, we have different options for dimensionality reduction. So here if I load the Plumbutter. So default, it's 4 dimensions and UMAP. So this is just what it does under the hood. If I set this to 3D, it'll make the color the 3rd dimension, but then the dot size is the same. And if I put it to 2D, this is the sort of old school way of representing where it's just X, Y, but now it's gray dots. So you have option between 2D, 3D, and 4D. In addition, you can now use the algorithm that's being used for the dimensionality reduction. So UMAP is the default, and it gives you this kind of folding manifold thing, which depending on the corpus that you have loaded, can look quite nice and is good for browsing. PCA is a bit of a cruder algorithm, but it gives you a different look of things. So if I put this to 4D, now PCA is interesting in that like the amount of dimensions doesn't change the lower dimensions. So you can see 4, 3, and 2, the 2 dimensions don't change just because of how principal components work. Whereas UMAP gets recomputed if it's 2, 3, or 4, you have a very different layout. But all of this put together means that you can have very different looks of the same exact data. So this is the Plumbutter corpus here. I can load with the amount of dimensions and an algorithm here, and that gives me this spatial layout. I can also do this, or this, or this, or this. And all of these are the same Plumbutter corpus, but just viewed in a different way. Now this is something I plan on making more use of in the future, but I need to do all these changes to Plotter to enable this. But for now, you get the perk of you have all these different ways that you can visualize the data that you're working with. And if you want a bit more info on UMAP and PCA, there's the Flucoma pages down here that you can look at. Okay, next up we have some changes to onset detection. So if I open up DK onset here, now if you want more information on this, you can look at the onset detection tutorial where I go into more detail. But in summary, you can switch between logarithmic and linear envelope modes, and that'll help you get onsets in certain kinds of material. So here I have a jazz ride pattern symbol. So if I use the default onset detection, this is what I get. It's getting some of the hits, but it's missing the dun, 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 dun. If I switch this over to linear, I now get this. So again, if you're curious, if you look at the onset detection tutorial, I explain this in more detail and show what's actually happening here. But to basically summarize, if you switch to linear mode, it's really good for detecting onsets in material that have like a kind of a sustaining core sound. So in this case, like a cymbal has like a kind of a roar sound that's just going the whole time. The linear mode will help differentiate that a little bit better. And then there's now also crosstalk, which is made specifically for using multiple mics at the same time, or specifically, I guess, multiple sensor percussion style microphones. So here I have a multi-channel file that's recorded. There's 4 channels of drum trigger audio and then 4 channels of microphone audio. We're going to be hearing the microphone audio, which is coming down this right side. And then the trigger audio is what's going down this left path here. So if I play some of this. So, we can hear some drum set sounds. So what's happening here is I have individual descriptor analysis going for each drum. So the kick, the snare, there's a ride and a tom. Sorry, a tom and then a ride. And then going into crosstalk like this, it means that when the kick triggers, it locks out the other ones from triggering at the same exact time. And when the snare triggers, it locks out the other ones from triggering at the same time. So this onset index here output is what tells you which drum has triggered first or per hit. So you can notice the different descriptor displays that are triggering at the bottom. So this is useful if you're using a bunch of them in parallel, but don't want them kind of doing crosstalk with each other. So the musical example here just has the same idea, but it's triggering different samples. So that sounds like this. So that's crosstalk. Okay, next we have a couple transient objects. So we have transient extract and transient replace. So transient extract is, I guess, similar to shatter in that it decomposes the audio, but this does it using specific transient decomposition algorithms. So in Flucoma, there's two algorithms. There's HPSS, which is harmonic percussive source separation, and transients. And each one has a different sound and character, but I'll show you the difference here. So I can turn each one of them off and on. So I have the percussive and the harmonic components, and I can switch the algorithms here. So I'll just play the gong drum. So this is HPSS. And if I switch to transients. So this is useful if I want to take something like this gong drum and I want to apply an effect only to the percussive components, so only this part. So I can apply just a reverb to that, but then leave this part unprocessed. So that's the general idea here. I find HPSS gives me a bigger transient, like more of the sort of audio. They aren't time-based. They do frequency. They do funky signal decomposition things, so it's not just slicing in time. But the HPSS gives me what I think is a bigger transient, whereas the transient extraction is just the little, just the tip. So that means we have a few different algorithms across data now. So you have the HPSS, you have transients, and then you also have shatter. So here I'll show you what they each sound like with this 2-synth voice thing from the Flucoma examples. So that's HPSS. Here's transients. And here's shatter. So each algorithm is tailored to a different thing, but you have different ways that you can decompose audio. And the way the algorithms are all built in Flucoma, they all null sum, meaning that if I have both of these components together, that is exactly the audio that you got before the algorithm. So there's no loss for having both enabled. You do get a little bit of latency because it's a time-based thing that's happening, but the audio will actually be exactly the same, which is quite good. So here's an example with selective processing. So the transient bit is being set to this like little dirty distortion thing, and I can use different algorithms here. So this is the transient one by default. If I set it to HPSS. And then finally, here's a musical example that's making use of all of that. So I'm sending the transients through this convolution and then a freeze. And then I'm sending the harmonic component through a different convolution and then overdrive. And on top of that, there's some kind of stuttering happening over here. So with transients, it sounds like this. And with HPSS, it sounds like this. So you can hear a big difference in the character of this kind of high bell in the convolution. So that's transient extract. Then we also have transient replace. This is inspired by the Slap plugin by Mr. Bill. So if you've not seen that, it's a quite interesting plugin. What it does onset detection. And because the onset detection in Datanaught is so fast, like on the order of a few samples, I thought that it would be cool to do onset detection in real time, but like in actual real time, not necessarily, because when you use a DAW and you use look ahead for your plugin compensation, you can do real time, but there's actually latency that you're not hearing. Here we're doing actual real time, meaning that when an onset's detected, I can replace the onset part of the audio with a different sound. So here I've got the onset detection that you can set your sensitivity as you normally would. Then you have an in and out, which is the envelope for the playback of the sample that's being triggered. And then we can have playback speed and start and length and all this. So if I load this transient chirp, so that's this one here. And if I play it back, I'm replacing the actual transient that's happening with this chirp sound. And I can set some of the parameters for it. So for example, I can change the speed of it. I can also change where it starts in the sample, how much of it it's playing. So you can do some really interesting sound design here. So here I'm almost getting like a kind of duct sub kick thing, which is kind of like pumping with the fading back. Because what it's doing, it's playing this, and then the envelope that you apply, so this fade in and fade out, is applying the inverse of the envelope to the sample. So if I load a different one here, here's a scream. Okay, and then there's different modes. So I can do full replacement, which is a default mode where it's actually just replacing the audio with new audio. Or I can do a layer. So I can, instead of replacing the audio, I'm adding it as an additional layer. So when I replace here, I'm actually fully removing that audio, so you get this kind of ducking sound happening with the acoustic audio. Now there's some options for randomization. So because this is happening at sample rate, you can't really do descriptor analysis or loudness analysis and map that over. It's happening like sample accurately and instantly. So in order to get some variation with sounds, you have these options to randomize some of the parameters. So by default, I'll just play a bit of this. Actually, I'll select in the middle here. So I'm playing this kind of piano scrape here. Now I'll put that to a bit of a shorter length here. Now I can randomize these parameters. So I'll have the speed be randomized every time it plays back. I can also randomize the start, which it's doing here by default, and the length is being randomized. So if I put the length back to what it was here, and I kind of randomize all of these, I'll get a random kind of contour happening with each of the hits. Which is cool for adding a bit of variation to each one of them. So the playback settings here, here there's some visualizer so we can picture what's happening. So this is the whole sample that's loaded, and then this is the section that's being played back. So if I set the length here, you can see that the kind of windows change accordingly. So if I put this to default here and play back, so I'm playing that much of this sample. Here I can see the amplitude envelope being applied at the top, and at the bottom I can see the playback envelope. So if I start massaging some of these values, and I'll start messing with some of the amplitude settings here, the envelope settings. You can see these different envelope shapes I'm applying there. But this starts getting quite quirky in that we have speed, curve, and symmetry for the playback. So we can affect the actual playback envelope. So there's the normal playback envelope. If I start applying a curve to it, you get that kind of pitch envelope that you do, like let's say if you're making a kick sound. So there I'm playing back the sample this way. I can also set a symmetry. And what symmetry will do, so if I put these back to default here, if I put this at here, it'll play reverse. And if I put it at 50, what it's going to do, it's going to play forward and then backwards. In this case, twice the speed because it's in the same period of time. So if I do something like this, it's going to play forward and then play reverse at the end. So again, you can do some interesting sound design. And this patch here is super useful for visualizing what's happening. So both in terms of the amplitude envelope and the playback envelope, because depending on the settings that you're doing, you get some really funky shapes happening here. So for the audio input, you can have multiple inputs. So you can load a sample and use transient replace like I've been showing for the previous examples. But instead of loading a sample, you can just use a different audio input. So in this case, there's noise going into this separate one. So if I do the replacing, rather than actually playing back a sample, I'm just doing audio input. So in this case, it's noise. I can maybe do a kick, or I can, kind of a sidechain input, meaning that nothing is going in. And I'm sort of sidechaining nothing, which is an interesting sound in and of itself. But you can use whatever audio input you want into here, which is really cool for, you can have a whole separate signal path going into there and do whatever you want. And then whether you have the replace mode or the layer mode, you can do some onset-based processing based on that. And then, like with before, the envelope in, out, and length is determined by that. So if I put this to sidechain, I'm basically adjusting the attack and release of a sidechain compressor, but with no actual sidechaining happening, just based on the triggers themselves. Here we have the probability in every that we have in, a lot of the onset-based things. So if I set it to 50%, or every third one, or a combination. So if I put it to every 5, and then there's a 25%. So every 5th hit, there's a 25% chance of it triggering. I can also do manual triggering. So I put it in manual mode and I have a separate trigger going in. So here I have a Wurlitzer playing back the whole time. Then I have these onset detection going on here with a very long lockout. So 1 second, it's triggering that. It's triggering some bounces, and then it's using those bounces at a manual sift. So that's going back and forth between 2 different reverbs. So combined, that sounds like this. So in this case, I'm getting kind of a funky sidechain effect from the sustain of a different sample, and that has its kind of a panned reverb thing happening at the same time. Then you have the different input modes. So if you're using a microphone, a contact mic, sensor percussion, if you want to do separate onset detection and the audio that's being replaced, you can do that. And then finally, here's a musical example that's combining a lot of these different things together. So we've got the bell sample loaded. We have random speed, random curve, random length. We have manual mode being triggered by a descriptor analysis. So whenever it's noisy or not, it will trigger the replacement, or it's going to go down here and trigger a specto sample of a completely separate transient replace with no actual audio input going into it in manual mode. So combined, that sounds like this. So that's transient replace. So finally, there's some quality of life things. So there's this Corpus cluster sampler. So that's just a combination of a bunch of the different objects, just the highest level of it. So if you just load this up, you can do the Corpus cluster sampling, but with a single object. So I just load that up. And then I can do the Corpus sampler, Corpus cluster sampler like I was doing before. All the matching objects now have an active message. That's something that I don't know why it took me that long to add, but if I go to corpusmatch, so if I load my corpus here, now there's this active message, which is by default on. So if I load a corpus, everything will work as it would. But let's say I want to stop matching rather than having to gate the messages or gate the audio, I can just toggle the active off. So that's across all the sort of event-based things. So corpus match, corpus cluster match, concatmatch, like basically all the objects that do any kind of matching now have an active message. All the ones that let you record stuff now have a train toggle. So this is for setup create. This is, I think I made this specifically for this one. Whereas before, so if I open up, where's setup create? So before it was just going all the time, which meant like if you had a microphone, it was just kind of capturing bits before you were ready. So we'd have to clear it by before you even started. So right now nothing's happening until I toggle this train message on, and then it'll capture the events. And when I'm done, I turn off train and then it registers everything. So just kind of reworked how that goes. And that's the case for all the objects in which that's relevant. The descriptors objects now have these select messages. So if I go to descriptors, so to say I'm only interested in having the loudness. So by default, you get loudness, the derivative of loudness, centroid, flatness, pitch confidence. You have all these different descriptors. But let's say I'm only interested in pitch, or I'm only interested in loudness or centroid. You can now set a select message. So if I set select loudness, the only thing that comes out of the bottom of the object is loudness. Or if I put here pitch and centroid, the only thing that comes out are pitch and centroid. Now, it's worth mentioning that the buffer output is unaffected, because if you're doing corpus-based matching or something like that, that always needs all the dimensions. So this only affects the list output, but you can select what you want to come out. Concat analysis, it's just faster now. I did some tidying on some of the built-in corpus stuff, so it just denoised and made things a little bit better sounding. Plotter can connect to all corpus playback objects now. Data looper now has an overdub function. So if I load data looper here, in addition to building up the layers of different bits of data, there's now a message here for overdub. So now you can just add additional layers of data to the data that's already recorded. Every was now added to probability. So probability can now do the probabilities it normally does, or every. There's now melband filter, which also goes now well with the spectral shape filter. So melband filter is this one. So it takes the output of melbands and then uses that to create a filter. So in this case, I'm taking the outputs of real-time melband analysis and then using that to apply a EQ filter to noise. So similar to what I showed with spectral shape filter earlier, but that's just built in now. And now finally, there's a patch for doing mic correction if you have histols installed. So if I go to the convolver help file, and if I go to tab here for mic correction, this explained and showed you the mic correction. So just to kind of remind you what this does. So here I have audio from a sensor percussion sensor. It doesn't sound great. I can correct it. Now it sounds better. So there's this patch here, microphone correction. So if I load this, you have to have the hiss impulse response toolbox installed for this to work properly. But now if you use this example here, you can create your own microphone correction. So if I hit record here and give it some audio, the idea being here that you have a reference microphone. So let's say either a nice microphone or a specific microphone in a certain position, and then the audio you want to correct. So in this case, let's say like you've got a nice condenser mic, but then you have a 57. That's what makes more sense live. or a contact mic or a sensor percussion microphone, whatever it is. You run that in, you hit record finish, and what this does, it takes this and generates an impulse response to correct the sound. So if this is something you're interested in, I recommend the Hiss Toolbox because you can do a lot more of this kind of thing with that, but I wanted to bundle something just for doing basic microphone correction, which is something that's useful with the built-in convolver. So there we go. That's what's new in version 1.0.
Das